In the last video, we finished up after executing all the implemented interface methods on the bird class. Let's continue on by creating another method in the main class, private static void in flight with a flight-enabled parameter. I'll make a call to flyer.takeoff and flyer.fly. If flyer is an instance of trackable, I'll call tracked.track. And finally, I'll call flyer.land. The argument to the method is something that flies. That is a flight-enabled type. I'm calling the takeoff and fly methods on that variable. After the flyer is flying, I want to track it if it's actually trackable. To test this, I'm using the instance of operator with pattern matching. You've seen and used this before, but it's important to take note that this is testing an interface type, trackable, and it still works the same. If the object is a class that implements trackable, then a local variable is set up named tracked with the type trackable. And because of that, I can call the track method on that variable. Next, I want to make a call to the inflight method from the main method. I'll comment out the last 4 lines, and I'll add that call to inflight instead. I'll pass flyer as an argument. Let's check the code output. We get the output bird is taking off, bird is flying, then we get the track method statement, bird's coordinates recorded, and finally bird is landing. So why couldn't I just have put all these methods on the abstract class animal or a subclass bird? Well, first of all, not all animals fly, and not all birds fly for that matter. I don't want all animals or birds to be tracked either. There are a lot of different things that fly and things we might want to track that aren't birds. Continuing on, I'm going to create another new class in our package called Jet. I'll have that class implement the same 2 interfaces. I think you'd agree with me that a bird and jet have very little in common besides flying and maybe having wings. But this is the beauty of interfaces. We can treat a bird and a jet similarly from the client code's perspective. What they actually do is dependent on how they implement the flight-enabled methods, but the client can treat them as if they were the same. Let's copy and paste the last 4 methods we had on bird and paste them into jet. Back to the main class's main method, I'll create an instance of the jet class. I'll just call the inflight method and pass it a new instance of jet. Let's try out this code. You can see that we're able to pass both a jet and a bird to a method that can use them, because both of these classes implement flight enabled. What's really nice is that you can mix and match interfaces as you need them. To demonstrate this, I'll create another class, this time called truck, in the same package. I'll add implements trackable. The class doesn't compile because I have to implement the track method on it. I'll copy the track method from bird and paste it here. Okay, so that's a truck, which isn't going to fly, but it might be tracked if it's used for moving freight around. I'm not going to call in flight for a truck in the main method. I'll create a new instance of truck. I'll call the truck.track method. I am calling this method from the truck variable, which I declared with the trackable type. Running this now. You can see that a truck can be tracked because it implements the trackable interface. Let's review what I did here. An interface lets us treat an instance of a single class as many different types. The bird class inherits behavior and attributes from animal because I used the extends keyword in the declaration of bird. Because the move method was abstract on animal, bird was required to implement it. The bird class implements the flight-enabled interface. This required the bird class to implement the takeoff, fly, and land methods, which were the abstract methods on flight-enabled. The bird class also implements the trackable interface. This required the bird class to implement the track method, which was the abstract method declared on trackable. Because of these declarations, any instance of the bird class can be treated as a bird. This means it has access to all of bird's methods, including all those from animal, flight-enabled, and trackable. An instance of bird can be treated like or declared as an animal with access to the animal functionality described in that class, but customized to bird. It can be used as a flight-enabled type with just the methods a flight-enabled type needs, but again customized for the bird. Or it can take the form of a trackable object and be tracked with specifics for the bird class. Interfaces let us take objects that may have almost nothing in common and write reusable code so we can process them all in a similar manner. On this slide, you can see that a jet, a bird and a dragonfly are very different entities, but because they implement flight enabled, we can treat them all as the same type, as something that flies and ignore the differences in the classes. Interfaces allow us to type our objects differently by behaviour only. Okay, so I have a few more things I want to cover, and this is best done in code. So let's add a field to the flight enabled interface. I'll add a miles to kilometres conversion rate and set it to 1.60934 and then kilometres to miles, assigning that the value 0.621371. Here I've created two fields, both doubles, and it looks like I've gone against the naming convention and used all uppercase letters with underscores between them. Why did I do this? Well, it turns out any fields declared on an interface are not really instance fields. They're implicitly public, static, and final, which means they're really constants. I haven't talked a whole lot about constants yet. I referred to them a little bit when I talked about the enum, but only briefly. When we use the final modifier, we prevent any further modifications to that component. A final method means it can't be overridden by a subclass. A final field means an object's field can't be reassigned or given a different value after its initialization. A final static field is a class field that can't be reassigned or given a different value after the class's initialization process. A final class can't be overridden, meaning no class can use it in the extends clause. A final variable in a block of code means that once it's assigned a value, any remaining code in the block can't change it. And a final method parameter means we can't assign a different value to that parameter in the method code block. I'll be covering each of these scenarios in turn, but right now I want to talk about the final static field, which is what you're really creating when you declare a field on an interface. A constant in Java is a variable that can't be changed. A constant variable is a final variable of primitive type or type string that is initialized with a constant expression. Constants in Java are usually named with all uppercase letters and with underscores between words. A static constant means we access it via the type name. We saw this with the integer.max_value and the integer.min_value fields. Java lets us specify these like an ordinary field on an interface, which might be kind of confusing and misleading to a new Java programmer, but we can declare them with any combination of those modifiers or none at all with the same result. These all mean the same thing on an interface. But coding it in IntelliJ, any of the statements with the exception of the first statement will give you the information that the modifiers are redundant. Let's go try that out. I'll add public static final in front of double. Notice that all three of those modifiers are grayed out in IntelliJ, and if we hover over any one of them, you can see that the modifier is redundant for interface members. I'll revert that last change. You can access these fields like you do with a class's static fields, using the type name and then the field name. I'll add some code that uses that constant to convert kilometres to miles. I'll add kilometres travelled and set the value to 100. For miles travelled, I'll multiply kilometres travelled by the constant kilometres to miles, and then I'll print both out using printf. We start with 100 kilometres, and I multiply that by the constant onFlight enabled, which is the conversion factor to go from kilometres to miles. I will run that code now to see the output. You can see that the truck travelled 100 kilometres or 62.14 miles. Okay, so that's fields on interfaces. It's important to remember that an interface never gets instantiated and won't have a subclass that gets instantiated either. There's no such thing as instance fields on an interface because of this. You might ask, isn't a bird an instance of flight enabled? The answer is no, not really. Bird is an instance of a class that implements flight enabled methods. Bird doesn't inherit traits from flight enabled, it just agrees to behave a certain way as defined in the abstract class. This video is starting to get long, and I still have a few more things to cover with interfaces, so I'll continue discussing interfaces in the next video.